All right, how are you guys doing?
Good.
Good? Amazing. Great. All right, I wanted to follow up with what we did last time. If you remember, what did we do last time again? Maximum and minimum, right? So today, just in the beginning of the lecture, I'm going to summarize the procedure for finding maxima and minima. To summarize with two M's? Yes. Summarize maximum and minimum finding. Suppose that you are given an example such as this. Find the maximum and minimum values of the function f of x equals x plus 1 over x on the interval 0.5 to 3. Okay? So you're only looking at this particular interval, not the whole real line. And we want to find the maximum and the minimum values. And here we mean the absolute maximum and minimum values, not the local maxima and minima, but the actual maxima and minima. The local ones are ones that you should be aware of that they might exist. But generally, you're interested in the actual maximum and minimum values of the function. Okay, so how do you do this? There's two steps. The first step is to find all critical points. Critical points. That is, all the points such that f prime of c is equal to 0, or if there are any, the points such that f prime of c does not exist. And also the endpoints. In other words, find all the points that might be suspicious. In this case, do we have any points where the derivative does not exist? What do you think? Are there any points where the derivative does not exist? Well, actually, we're good because we have a lot of theorems that guarantee that such a function is actually very well behaved. And it's continuous, and a derivative exists anywhere this domain is defined. So the only point that will be funny and weird will be 1 over x for 1 over x when x equals 0, right? But 0 is not in the domain. So we're good. Okay? So no points where f prime of c does not exist. This is something you need to worry about more for piecewise defined functions and things like that. Or, for example, absolute value. The absolute value function has a corner. At that point, the derivative is not defined. For a function like this, you're more concerned about the points where the derivative is equal to 0. The derivative of this function is equal to 1 plus minus 1 times 1 over x squared. So we said it's equal to 0. That means that 1 is equal to 1 over x squared, or x squared is equal to 1. That means that there's 2 points that satisfy the equation. There is x equals, what do you think? X equals 1 and x equals minus 1. Okay, but there's one point that I don't need to worry about. Which one is that? Negative 1. Why not? It's not in the domain. So I don't need to worry about this point. I cross it out. Okay. And I also need to worry about the endpoints. The endpoints are x equals 0.5 and x equals 3. Okay, so now I collected all my potential maxima and minima, all the points that could be maxima and minima. And now what? That's step 2 now, is to evaluate the function at each of those potential or suspect points. So evaluate f of x at each such point. So for example, f of 1 is equal to 1 plus 1 over 1, that's just 2. F of 0.5 is equal to 1 half plus 1 over 1 half. Now, divided by 1 half is the same thing as multiplying by 2. So this is equal to, oh, I'm sorry, did I write something? Yeah, sure. So this is 1 half plus 2 is equal to 2.5. And finally, f of 3 is equal to 3 plus 1 over 3. And this is roughly 3.33. Okay, and at this point, you look at the values of each of the function at each of the points, and you evaluate which one is the largest one and which one is the smallest one. Which one is the largest one? So that means that this is the maximum, and this is the minimum. Simple as that. Because the maximum has to be there by a theorem that we proved. Remember, there's a theorem, well, we actually didn't prove it, but we stated it. If the function is continuous, it has to have a maximum or a minimum. And that maximum and minimum have to be critical points. So they have to be a suspect. If we check all the suspects and we look at the minimum value, it's got to be in there. Okay. And similarly, the maximum is there. So it's really simple when it boils down to it. When you use all the theorems, it really boils down to this procedure. Find all the suspects and then evaluate the function at each of those points. Okay, questions? Yes?
When finding the critical point,
yes?
how did you get the negative multiple of x squared equals 3?
Because you're looking for all the points, all the values of x that satisfy that x squared is equal to 1. And so it could be 1 or minus 1. If you plug in x equals minus 1 into that equation, you get 1. Minus 1 cannot, we don't consider the point x equals minus 1 because it is not in the domain, in the interval from 0.5 to 3. Okay? Any other question? Arn?
Is f of 2.5 equal to 2.5? Is that a local point or a local?
Good question. What happens with f of 0.5, which is equal to 2.5? It could be, in this case, it cannot be a local maximum. Well, you know what? It could be a local point. It could be a local maximum or minimum, because the function might start doing something like this, right? So locally around this area, it's a minimum, right? So yeah, it could be a lot of things. It could be a saddle, for example. It could be a point where the function kind of slows down and then picks up again. So there are many things that could be going on with those intermediate values, with those intermediate points. You would need to look closely at the function, more closely. Okay? Any other questions? Okay, great. So that's it. So now, let's talk about section 4.2. Which is about something called the mean value theorem. Mean value theorem is a theorem that you see over and over again in several situations in calculus. It's just like a Swiss Army knife of theorems. You kind of use it here and there every once in a while, especially when you're proving things. Okay, so you might think, well, it's for proof, so I don't care. No, it's actually a useful theorem to know, and it's so important that the book dedicates a whole section to it. So it better be good for something. The statement turns out to be very simple, especially graphically. So let me first tell you graphically what the statement is. You will tell me if you agree or not with the statement, and then we'll go into the math. So, suppose that you have a function, any function f, defined from a to b. And this being a calculus course, we're going to assume that the function is differentiable. Okay? Now, I'm going to draw a line from one endpoint to the other endpoint. So this is not a tangent line, right? It's just a line that goes from one endpoint to the other endpoint. Let's call this line L. And just for kicks, what is the slope of L?
FB minus FA over B minus A.
What's the slope of L? Okay.
Minus FA over B minus A.
F of B minus F of A, that's right, divided by B minus A. Does everybody agree? The slope is the rise over the run. The rise is F of B minus F of A. The run is B minus A. Okay, so I want you to look at the tangent lines. Now I want you to look at the tangent lines of the function f at different points. For example, over here, I could draw a tangent line. I'm not going to draw it, but I could draw it, and it looks like this. Over here, it looks like this. Over here, it looks like this. Okay? And what I want you to think is, to ask yourselves, is there any tangent lines that are parallel to L? Once again, you can draw tangent lines all over the place at different points of the function. Question, is there any tangent lines that are parallel to L? What do you think? Yes. There are, right? So for example, I mean, I guess I could ask you to point, but it's going to be hard for you to point on the right location. Okay, let me ask you this way. Do you think there's only one point, or can there be more than one point in this case? There's actually more than one. There's how many? Two. There's two. That's right. You got it. So the 2 points are somewhere in here. And if you drew the tangent line, you would get something like this. And another point is over here, where if you drew the tangent line, it would look something like this. So that's the funny thing about this theorem. It basically says, and that's really the statement of the theorem, it says that there are points where the tangent line is parallel to L, to that particular segment. You say, well, what does that mean? What is that useful for? Well, it turns out it's actually quite useful for several different things, as you're going to see in a moment. But let's just make the statement more clear. So this will be a point C. Okay? At some point C, the tangent line is parallel to L. Now, let me rip this page off. And then, what do you guys think? How can we make more precise this idea of being parallel to a line? Remember, we're in a calculus class. So what do you think we're going to write when we talk about being parallel? Exactly. So whatever number this is, the derivative has to be equal to that. Right? Great. That's where we're heading. So, notice there exists C in the interval AB such that the tangent line at C is parallel to L. That is, okay, and now let me just make this, this statement more precise. Parallel to L is just a bunch of words. If you wanted to write this in an equation, the way to do it is to say that the slope of L is equal to the slope of the tangent, right? That's the same thing as saying that the two lines are parallel, is to say that they have the same slope. So that means that f prime of C is equal to f of B minus f of A over B minus A. Okay, great. All right, and that's actually the statement of the theorem. Let me make the statement of the theorem more clear. It says mean value theorem. Suppose f is continuous on an interval AB. Notice that I'm including A and B. So these are square brackets. And differentiable on the round interval A to B. In other words, differentiable at every point strictly between A and B. Okay, the reason we do square brackets and round brackets is because we don't want to deal with differentiability at the endpoints. I'm not asking anything from in here about whether f is differentiable at A, because we don't even know what that means. It's sitting in there in a corner, so we don't want to deal with that. But this we know what it means. It's continuous at every point in this interval. And this we also know what it means. It's at every point between A and B, you know, less than B and bigger than A, the function is differentiable. Okay, these are the hypotheses of the theorem. And the conclusion is, then there exists C in AB such that f prime of C is equal to f of B minus f of A divided by B minus A. Okay, so that's the theorem. And we're going to use the theorem for a couple of things. But first, I would like to say a few comments about what it says and what it does not say. So, notes. Does the theorem tell us how to compute this point, or what that point is? Does it say the point is like the average between A and B, or is it like a third away, or anything like that? There's no actual formula for where C is. The theorem only says there exists C. You would think that's a pretty weak statement. You wouldn't know what to do with that thing. You know, I know that there's a C, but I don't know where it is, so how good is that? But as it turns out, that is useful, to know that it exists, even if you don't know where it is. So we don't know the value of C, only that it exists. First statement. Second of all, could there be more than one point C satisfying that condition? Well, we saw in that example, yes, there can be more than one point. There could be more than one C. Or more than one such value. Okay. So let's see. I'm going to give you an example. All right, let's do an example from the book, just to make sure. Just one random function, and then verify that yeah, okay. So f of x equal to x squared minus 2x plus 5. And the interval is let's say 1, 3. Okay, this is just one example. Any function would work. Okay, so f prime of x is equal to 2x minus 2, and f of b minus f of a divided by b minus a is equal to what? Well, let's see. We first have to evaluate f at 3, right? That is, what is, so that's 3 to the 2 is 9, minus 2 times 3, which is 6, plus 5, minus, and the same thing evaluated at 1, it's 1 squared is 1, minus 2 plus 5. The whole thing divided by 3 minus 1 is equal to, let's see, so this is 6, so 9 minus 6 is 3, plus 5 is 8, minus, and this is 5 minus 2 is 3, plus 1 is 4, divided by 3 minus 1, it's 4 divided by 2, is equal to 2. Look at that. So, there should exist some value between 1 and 3 such that 2x minus 2 is equal to 2. Such that 2 times c minus 2 is equal to 2. Okay, that's what the theorem says. There should exist such a point. And when we solve for this, we get 2c is equal to 4. So c is equal to 2. And 2 is between 1 and 3, right? Great. All right, so this is just an example of the theorem in action. But it's not a very, I mean, it just shows that it's true in this particular case. The theorem says it's true in any other case. And that's it. Okay. So now let's do a couple of applications of this theorem. And if we have time, we'll try and prove it. Okay, the first example is, suppose that you're driving, a car is driving along a highway. But don't think about the car driving on a uniform speed. The car may be sometimes stopping, speeding up. You know, there's no guarantee that you're driving all the time at the same speed. So you start, let's say, at 0. and you start driving, traffic moves around, you have to stop sometimes, you have to go again, something like that. And then eventually you get to your destination. Right here. Suppose the whole thing took 2 hours. And the whole distance covered is 120 miles. So a car drives for 2 hours on a highway. At varying speeds. Okay. Covering 120 miles. Total. Show that at some point its speed was exactly 60 miles per hour. Okay, so that's somewhat surprising. You don't know how fast the car is going. The car was slowing, stopping. Sometimes it was going way faster than 60, for example, it could be. Sometimes it was going at 0. It was stopping on the traffic. But mathematically, we can say that at some point, the car was exactly at 60 miles per hour. Okay, how can we say that? Well, so suppose that the function f describes the position of the car at time t. Okay, let's call it, you want to call it f of t? No, f of x is fine. So x is the time. All right, fine. So a is equal to 0. B is equal to 2 for 2 hours. And f of 0 is equal to 0. And f of 120 is equal to, I'm sorry, f of 2 is equal to 120. F of 2 is 120. Okay. So, this is what you can say, by the mean value theorem, there exists C such that the velocity at time c, that's f prime of c, right? The velocity is f prime of c, is equal to f of 2 minus f of 0 divided by 2 minus 0. But that is 120 minus 0 divided by 2 is equal to 60. That's it. So the proof is a simple application of the mean value theorem. At some point in time, the speed of the car was exactly 60 miles per hour. Okay? Great. All right. By the way, in this example, we have an interpretation for the quantity f of b minus f of a divided by b minus a. So if b is the distance covered, what do you think is f of b minus f of a divided by b minus a? What is it? Miles per hour, yes. What is that? Speed. Velocity.
Antiderivative of acceleration.
No. Okay. Overall, it took you 2 hours, and overall, you drove for 120 miles.
Average speed.
Yes, the average speed. The average speed. You've done calculus for so long that that you forgot about the more basic ideas. This is where we started. We started talking about average speeds. Okay, so you drove for 120 miles. It took you 2 hours, so on average, you drove at 60 miles an hour. So this statement is actually more general. If you're driving from point A to point B, then there exists a point in time where the exact speed at that point is the average speed over the whole thing. That's a cool thing to know, I think. Maybe. Maybe not. Sorry. Anyway, that's the theorem. Okay, so now let's use this for slightly more theoretical analysis. For example, suppose f of 2 is equal to 5 and f prime of x is less or equal than 3 on the interval 2 to 4. Okay, so this looks like it has nothing to do with the mean value theorem, but it actually does. So here's the idea. Suppose that you have a function. The function has value 5 at 2, okay? And you have a bound, in other words, you know how fast the function can possibly grow, anywhere between 2 and 4. So question, how wildly varying could the function f be? How large could the function be at 4? Do you think, just from your intuition, do you think that if the derivative is always less or equal than 3, do you think that f of 4 could be equal to 100? It doesn't make sense, right? If the derivative is always less or equal than 3, and f of 2 is 5, then f of 4 could not be 100. But how do you prove it? Sorry? Maybe, but you don't know anything. The suggestion is to prove it using maximum and minimum values. But you don't know anything about the function, right? You don't know anything about f of 4. You really only know this information. So as it turns out, the mean value theorem is a useful tool to bound a function if you know this kind of information. So find the largest value that f of 4 can have. It's kind of a strange question. You know the value of the function at one point, and you know the derivative. You know something about the derivative. Find the largest value that f of 4 can have. And intuitively, see if this is 2 and this is 4, and the function at 2 has this value, the function could not possibly be like 2 sloped, right? Because what would happen if the function was way, way, way large at 4? Then that means that the derivative has to be really big, right? But we know that the derivative is less or equal than 3. Right? Do you see how this argument would work? Generally, I think in math that the best thing to do, like when you reach a really good level for solving problems, is when you can see the problem as intuitively obvious, and then you use your available tools to prove it. So I think it would be good for you to see first, this has got to be true. You know, f cannot be really equal to 100 or 80 or something like that, because otherwise the slope would be too large. And we know that the slope is less or equal than 3. Okay? Just out of your intuition, what do you think what would be the largest value for f of 4? Eric?
So it would be 5 plus your slope is
3 at
I'd
most.
say largest value would be 3. So there's 2 points in between, so that would be rise of around 3. Wait, hold on.
Wait, so Eric is saying, let's say that function increases at the maximum possible rate. Okay, let's say that f prime is 3. That's the fastest the function can grow, right? So the maximum value 1 unit further at the point 3 will be 5 plus 3, which is 8.
And then plus 3.
And then another 3, that's 11, right? So we think, right, the maximum value the function can have at 4 is 11. So let's use the mean value theorem. Okay, there exists C in 2, 4 such that these two things stands for such that f prime of C is equal to f of 4 minus f of 2 divided by 4 minus 2. Okay, so that means that f prime of C is equal to, and we don't know what f of 4 is, but so let's leave it like that, minus f of 2 is what? 5 divided by 2. Okay, so that means that f of 4 minus 5 is equal to 2 times f prime of C, right? But we know that this thing is less or equal than 3. So the whole thing multiplied by 2 is less or equal than 6. Do you agree? If this number is less or equal than 3, then the product is less or equal than 6. That means that f of 4 minus 5 is less or equal than 6. And if I add 5 on both sides, I get f of 4 is less or equal than 11. This is the maximum possible value that f of 4 can have. Okay. Questions? All right. So now let's do a more general application. We're going to prove a couple of things that are obvious, but if I ask you to prove it, we would not know how to even start the proof or how to go about proving it. So for example, suppose that f is continuous on AB differentiable on AB open, round interval, and f prime of x is equal to 0. For every x in AB. And this is round. Okay, suppose that the derivative of a function is always equal to 0. Then what do we know about the function? It's constant, right? Then f is constant on AB. Okay, so that's a statement that if you've seen some calculus before in high school, you would think, okay, this is obvious. If the derivative is 0, that means the function is flat. The graph of the function is flat all over the place, so it's got to be a constant. Right? So you say obvious. Well, no. You need a proof, right? So how do we prove this thing?
Point slope.
Sorry?
Use a point and slope. Y.
Use the point slope.
Yeah, y1 is b and y.
No, but you can't use this point slope formula because we don't know that the function is a straight line. The function could be anything, right?
This yb equal y, so it's like.
Okay, let's use the mean value theorem. Suppose how should I say this? Suppose f is not constant. Okay, if a function is not constant, that means that there has to exist 2 points. Let's give these things names. I'm not sure how to call them, but D and E. How's that? Okay, so that means that f of D is different from f of E for some D, E in A, in AB. Okay, suppose the function is not constant. So there's got to be 2 points where the function has different values, right? Okay. By the mean value theorem, there exists C in the interval DE such that f prime of C is equal to f of E minus f of D divided by E minus D. Okay, now we said that f of D is different from f of E, right? That means that this whole thing cannot be equal to 0. Because the only way this can be equal to 0 is if the top part is 0. In other words, that f of E is equal to f of D. So this thing is different from 0. And this violates the assumption that f prime of x is equal to 0. This is what you would call a proof by contradiction. Okay? Suppose that the function is not constant, and then we reach a contradiction, so what we assume cannot be true. There you go. And in the end of the proof, we can write a little square to make sure it's clear to everybody that we finished the proof. All right. Yeah, okay, I'm running out of time. I think we have just 1 minute left, so I'm going to leave it there. But no, you know what? No, let me just state this. Just take just a moment. So if f prime of x is equal to g prime of x for all x in an interval, then f and g differ by a constant. Okay? This is another statement that you're used to seeing all over in calculus. If two functions have the same derivative, then they are equal to each other except by a constant. Okay? And the proof is apply previous theorem to the function f minus g. Okay? So the function f minus g has derivative 0 because f prime is equal to g prime. And so by this theorem, the difference has to be a constant. So the two functions differ by a constant. And that's it.